All right, good afternoon. The plan today is for me to go over any questions you have from the homework or the practice problems from yesterday. Then we have a short lesson which is all qualitative in nature. It's all about information related to the next model of the atom and how it was developed and what the problems with the next model of the atom are. So at the end of this next lesson, there's no practice attached to it. So anytime we have left over, you can use to prepare for the rewrite exam, which is tomorrow in class. The purpose of Millikan's oil drop experiment is to determine the charge on those particles that Thomson discovered. In other words, the purpose is to determine the elementary charge or the charge on the electron. Millikan doesn't actually directly determine the charge of an electron. What he does is he determines the charge on an incredibly large number of different objects. They happen to be little droplets of oil. And in the end, we'll get to the equations in a second, but in the end, what he does is he looks at all of the charges that he gets and he asks himself, what are they all a multiple of? There's some number that they are all a multiple of. And what it really boils down to is he's looking for a factor, the greatest common factor of all of those numbers. He's looking for the biggest number that if you multiplied it by 1 or 2 or 3 or 4 or 5, etc., you would always get the values that he got. And if you think about it a little bit, it should become clear to you that the charges that he measures must be pretty tiny. Because if he measures a charge to be half of a coulomb, there's no way you're going to look at the number 0.5 and see that it's a multiple of 1.6 times 10 to the negative 19. It just can't be done. So the charges that he measures are quite small. He does it by, we don't need to worry about the exact details. He does it by essentially balancing an electric force with the gravitational force. So this diagram on the left is what he's doing. He sprays a fine mist of oil droplets into his apparatus. There's 2 parallel plates which produce an electric field. In the process, those particles become charged. Those little spheres of oil become charged. So there's an electric force up, there's a gravitational force down, and he adjusts the voltage until the drop is suspended. And if the drop is suspended, I'll show this derivation here, you're dealing with balanced forces, and you could write that the electric force, which is QE, is equal to the gravitational force, which is mg, and that's enough for him to be able to calculate Q on that oil drop. You can calculate the electric field by taking the voltage divided by the distance. He knows what G has a value of, 9.81, or whatever the value of it was wherever he was doing the experiment. If it was here in Edmonton, it would be 9.81. If it was in Calgary, it would be 9.80. It varies, but he takes that into account. And the only tricky thing is the mass, and what we've said is at this level, the mass of the drop is determined typically by looking at the density of the oil and the diameter of the drop, and you can use the diameter of the drop to find the volume of the drop, and use the volume of the drop along with the density to find the mass. In reality, he determines the mass by measuring the terminal velocity of the drop. It's pretty complicated for high school, though. You're also expected to be able to do force analyses in 3 other situations. By the way, when we did this yesterday, we looked at this situation, and then we looked at 4 others. But I don't know which page it's on, but at the top of one of the pages, you had those 4 situations. Under the heading, what if the drop is not suspended? The very first one has the drop moving with a constant speed, and there's no difference, physically speaking, in terms of physics is what I mean, between a drop that's suspended or one that's moving at a constant speed. It might even be moving at an angle at a constant speed. But if it's moving at a constant speed, that means the forces are still balanced. You have to be able to solve problems where the drop accelerates up, and if it accelerates up, the electric force must be larger in magnitude than the gravitational. If it accelerates down, there's two possibilities. It could be accelerating down at what I would peg to be about 18 meters per second squared for this last one, and at meters per second squared. And for this one, I would peg it at around 4 meters per second squared downward. These two are very similar. Well, actually, this one here and this one here are very similar in that you have opposing forces, but because one has a net acceleration up and the other has a net acceleration down, you have to subtract them in the order of biggest minus smallest. It won't work otherwise. And then, of course, if it accelerates down at 18 or whatever this is meters per second squared, these two forces, the magnitudes of them will be added together to get the net force, which would be ma. I suspect that some of you have questions regarding the problems that were assigned, so take a look at your work, please. Questions? Go ahead. Sorry? 7? So we have an oil drop that has a charge. You're told the charge in terms of elementary charges. Oh, this is a good question. You're told the charge in terms of elementary charges, not in terms of coulombs, but it's very easy to figure out what that charge is. We can take 5 multiplied by 1.60 times 10 to the negative 19 coulombs and get, I believe, 8 times 10 to the negative 19 coulombs. And this drop is suspended at 175 volts. On the other hand, we have a different drop that's in between the same parallel plates. So we haven't changed the distance between the plates. And this charge is 3, I think I saw 3, yeah, 3 elementary charges. And that works out to, and I'm just going to ask everybody to confirm my 2 values for the charges here. I'm pretty sure that's right. Okay. And we're asked what voltage would be required to suspend this. So I know the answer is right there staring us in the eyes, but the voltage has to be greater. And the reason the voltage has to be greater than 175 is there's less charge. And the electric force is going to be equal to the gravitational force no matter what. And the electric force is charge times electric field strength. So if the electric field strength, I'll back up, if the charge is smaller, you're going to need a larger electric field strength. There's so many different ways to solve this problem. So one of the things you could do, for both of these, we can write Fg equals Fe, which means that Mg equals Q. Are you okay with me jumping ahead and just saying voltage over distance? Okay. The problem here is that you are missing too many variables. You can't do a direct calculation. You don't know the mass. You don't know the distance. But what you can do is this, and I think this is the best way to solve this kind of problem. In this setup, what doesn't change from the first to the second situation? What's something in this formula that is the same for both of these drops? Ethan? The density, but the density isn't in this formula. I'm looking for something specifically in this formula that doesn't change. Ben? The mass. It says an oil drop of the same mass. And even if it didn't, it would probably say if the same oil drop is given a different charge. So the mass is the same. What else is the same in this formula? Farhan? G is going to be the same. And there's one third one, the distance between the plates. So what I'm going to do is I'm going to rearrange this equation for all of the constants. And we've done this kind of thing before, just not with Millikan's oil drop experiment. So I end up with this. And all of these are constant. The left-hand side of this equation is constant. And the reason the left-hand side is constant is it's composed of three things that don't change. But that means this has to be constant as well, because it's equal to that other stuff, and the other stuff doesn't change. This is a little subtle, but the left-hand side of this equation is constant because M is constant, and G is constant, and D is constant. The right-hand side of the equation is constant because if the charge is less, the voltage has to be greater. They're going to change in such a way as to produce a constant product. They're both changing, but if one gets bigger, the other gets smaller. So now what we can do here, Sienna, is we could write, I'm just going to get rid of this to give myself a little bit of room. We can write that Q times the voltage here has to equal Q times the voltage here. And, you know, how many of you, I don't know if there's anybody who will say yes to this, but how many of you intuitively, I'm going to change the numbers just to make my point easier. Let's imagine this were 6. All right? How many of you intuitively would say, since we have half the charge, we're going to need twice the voltage? That's what's going to happen here. It's an inverse relationship. So if you're really good with numbers, I suppose you could say something like, since we only have 3/5 of the charge, we're going to have 5/3 of the voltage. But anyway, Sienna, you're going to put in the charge and the voltage, the charge and the voltage, and solve for the voltage. Does that make sense? There might be other ways to do it. I think that's the best utility method that I can give you that's going to work for all problems that are like this. Other questions? Yep. So the graphical analysis. And I expect that. I've never thrown this out here to a class and then everybody just goes, oh, no, I get it. This is a learning experience. So what's the setup here? You have a Millikan oil drop experiment. You have a constant mass in all of these data points that are going to be appearing on the graph. And the plates are a certain distance apart. That's a constant in the experiment as well. When the sphere is in the region between the plates, it experiences an upward acceleration, k. Just a second. That's pretty important. That's the big picture in physics. The big picture in physics here is that the net force would be the electric force's magnitude minus the gravitational force's magnitude. In this statement, you have to understand that that means there must be an electric force up. It means that the electric force up must be greater than the gravitational force down. So it is, to look at a diagram here, it is the second diagram on this screen right now from left to right. And we're going to need that in order to understand the graphical, where am I? In order to understand the meaning of the graph. So it experiences an upward acceleration, and the student varies the voltage and measures the corresponding acceleration. Look, if the electric force is up and you increase the voltage, you're going to get a stronger electric field, which means the electric force on the particle will be greater upwards. And the gravitational force is constant because it's the same mass. It's not even a different drop. We're using the same drop each time. We're just changing the voltage. So if the electric force goes up with the voltage, the net force will go up with the voltage. The acceleration will go up with the voltage. And they plot acceleration on the vertical axis and voltage between the plates on the horizontal axis. I have taught you, and I started this way back near the beginning of Unit 2, that you have to associate the quantity on the vertical axis with y. Like what we want to do, everybody, is we want to tie this physics equation somehow to y equals mx plus b. And I'm not even sure yet, well I am because I know where it's going, I'm not even sure where the y is in this equation. I might have to rearrange this equation to get my y by itself. And I will. Y is the acceleration, right? And x is the voltage. So I have to take my physics and somehow change it to this. I'm not going to put delta v, I'm just going to put v. My v is x, my y is a. So how do I do that? Well, I take this equation here. I'll do it above. F net is ma. Fe is q times voltage over distance. And minus Fg, well, that's mg. And I took the liberty of going from QE and then saying electric field strength is voltage over distance. You can see that that formula at the top of the screen that I wrote that says MA is just one mathematical operation away from being A equals. I need to divide everything in that top equation by M. So what I'm going to do now is I'm going to divide this by M, I'm going to divide this by M, I'm going to divide this by M. Because I want to get A by itself. And what I end up with for this term after the equal sign is Q times the voltage over mass times the distance. But I've already got the voltage here, which means that this thing in the box is Q over mass times the distance between the plates. And I hope it's clear that that's the slope. The slope of your line will have a value that's equal to the charge over the mass times the distance between the plates. When I divide the second term by M, I get G. I get G. So G is the negative of the y-intercept. I actually get, if you want to be really clear about it, I get negative G, don't I? So the y-intercept is negative G. And now, I mean, I'm not even going to look at the questions yet. There are going to be questions here that we're going to require looking at the y-intercept. We're going to require looking at the slope. We're going to need the equation of the line of best fit. And I think the best way to do that is to find 2 points. So I've prepared for this because I know people always ask about it, is to pick 2 points that you could read fairly accurately. To identify the coordinates of those points and do a linear regression. I don't think we need to start drawing triangles and finding the slope by going rise over run. I mean, if we do that, then we have to get into a mathematics lesson about how to find the y-intercept from that. And it's not difficult, but that's not why we're here. If you do a linear regression, and I'm not going to, you put in list 1, 66 volts and 74 volts, and in list 2, 1 meter per second squared and 2.3 meters per second squared, and you do a linear regression, you're going to get this equation. And knowing that that equation is equivalent to acceleration equals Q over md times the voltage plus the y-intercept is enough for you to be able to answer any of the questions. And we're going to go through some of them. I'm not just hand-waving it away. Okay? So I'm going to copy this because I'm going to need it multiple times, unless I did it already. Oh, I already got it there. Don't forget, this is it'll work. This is A equals Q over M times the distance between the plates times the voltage plus, well, minus G. So right away, you know what G is. The experimental value of the acceleration due to gravity is 9.7 meters per second squared. And I think that's a question here someplace. There it is, number 13. If we look at number 10, what's the voltage required? Oh, 10 is a tricky one. What's the voltage required to balance the sphere? Okay, if you're balancing the sphere, then the acceleration is 0. You don't need to overanalyze the physics of it. All you need to do is say, if the sphere is balanced, it's not accelerating up or down. By the way, this will be the x-intercept of the graph. Because if the graph is above the x-axis, it's accelerating up. And even though it's not part of the question, if we went to a lower voltage, it would be accelerating down. And that data point would be on the line. It would just be below the axis. So what you need to do here is solve this equation, which I hope you see that I've just changed y to 0, so you're finding the x-intercept mathematically. And that would mean you take 9.725, when you move it over it becomes positive, and divide by 0.16, and you're going to get around 60 volts, but that's just the rough back of the envelope calculation. The slope, oh, that's easy. It's 0.16, right? You would format it so that it fits that notation. So it would be, I just want to make sure nobody gets burned on this on an exam. If it's 0.16, for a value, it's 1.6 times 10 to the negative 1. We have to make it match the template in the question. And it's not asking for this whole thing. It's simply asking for these two digits. So you would enter 16. Doesn't mean the slope is 16. What's the charge on the sphere? Okay, so now what you need to do is ask yourself what feature of the graph contains the charge, and it's the slope. The slope is contained in that bundle of constants which are constant in the experiment. So the slope, which is 0.1625, has to be equal to the charge over the mass times the distance between the plates, which, I mean, you have to be told these numbers. I just have to go back and look at them. The mass is 2.63 times 10 to the negative 17. Let's see if I can remember these numbers. 2.63 times 10 to the negative 17. (2.63 times 10 to the negative 17). I'm not going to worry about the units. Was the distance between the plates 15 centimeters? Okay. So if we take the slope times the product of those two numbers, or times those two numbers, we will get the charge. And I'm not going to, do that on the calculator. You can do that, I think. That's 10. That's 11. That's 12. We did 13. I think that's it. No, 14. So you have to remember here, of these two equations, y equals 0.1625x minus 9.735. 9.725. Of this equation and the physics equation, you don't use the physics equation, you use this equation. It's saying you have a graph and you have half of a data point. What's the other half of the data point? It's telling you, oh, this is a little tricky though. If the acceleration is negative 4.6, because it's accelerating down, you have to use negative 4.6. And again, this graph, if you extended it, would look like a photoelectric effect graph, actually. And this really makes a lot of sense because this is zero voltage, and if there's no voltage, there's no force, so the acceleration is determined by gravity, which is why this is negative g. So you're going to be looking at negative 4.6 here and finding the voltage. You're just going to put negative 4.6 in for y. And solve for x because x is the voltage. And I suspect Liam and many other people in the room that once I had this entire explanation, which culminates, what's going on now? There it is, which culminates in this, I've kind of opened the door for you knowing what to do. All right, we're going to move on now and look at the next model of the atom today, which deals with the Rutherford model of the atom. Maybe I will do this just to take you back in time a few days. We started off with different models of the atom by describing the Dalton model of the atom, which is loosely called the billiard ball model of the atom. The problem with it is it's just too childlike. It's too simple. It doesn't take into account the presence of electrons, and it has to take into account the presence of electrons because Thomson discovered electrons, right? So you can't have a new discovery in science and then just ignore it and go, that's okay, I like this one better. It's easier. It's like Richard Feynman says, you know, the world is complicated. You have to be able to explain the way it really is, not the way you would like it to be. So atoms are not like this. Well, atoms are not like this either, but atoms are more like this than they are like Dalton's model. When Thomson discovered the electron, the prevailing scientific opinion said, well, we have to take electrons into account. Electrons are negative. We know from experiments they're very, very tiny. So let's just imagine that there are these tiny little spheres of negative electricity embedded within this big honkin' sphere of positive electricity, whatever that means. Now, it turns out, and I'm cutting to the chase here, that we're going to discuss an experiment today which is called Rutherford's alpha scattering experiment. And if atoms are like this, then the alpha particles that are going to be scattered in the experiment would be scattered in a totally different way than they really are. There's no way that these atoms can scatter alpha particles the way alpha particles are scattered. Okay? And the mathematics behind this whole lesson and his model of the atom and this scattering experiment is very, very complicated. I went back and looked at my notes from university, and it's like, I don't really understand what I was writing down now. I'm sure it made sense at the time, but it's very complicated. So I'm trying to teach this to you in a very intuitive way, a way that just makes sense to you. We're going to understand that the results of Rutherford's alpha scattering experiment lead to an improvement on the model of the atom, and then we have to be able to describe that model of the atom. We are also going to, I don't have it here, it doesn't matter, we're also going to talk today about the problems with Rutherford's model of the atom, because it's not perfect as well. And that's just an introduction to what's wrong with Rutherford's model of the atom that will ease us into the lesson tomorrow. So in 1911, about 110 years ago, Rutherford designed experiments where he could kind of look inside of an atom. Now, when I say peek or look, he's not actually seeing anything. But what he's going to do is interact with the atom in some way, and based on what he observes happens, he concludes what is going on in the atom. I forget who gave me this analogy. It might have been a physics prof in university. It would be like you coming into class one day and all the desks are gone, and there's somehow I've got a huge, huge sheet of plywood that's like 20 feet by 15 feet, and it's on the floor, but it's suspended by little table legs in the corners, and it's light enough that it supports itself. And I've got stuff under there, but you're not allowed to look under there to tell me what's there. And you have to design an experiment to tell me the nature of what's under there. Well, what you could do, I could get all of you to line up here. I could give you each a marble, and you could roll a marble from the front of the room to the back of the room. And you could observe where the marbles emerge from the other side. And if they all came out exactly where you rolled them, you would conclude that there's nothing under there. Yes? I would assume. I mean, maybe you happen to miss something. Maybe there was an obstacle and you missed it. But you would fire these marbles in all kinds of locations. If, on the other hand, you rolled the marbles and you heard this soft thud and they all stopped, you would assume that it's hitting something very soft and there's a soft barrier there. If they all bounced back, you would assume there's something very rigid. If some of them bounced back, but most of them made it through, you would conclude that there's something under there, but it's not everywhere. There's a little barrier over here, and there's a little barrier there, and there's a little barrier there. And you start to get an idea of what the structure of whatever is occupying the space looks like. Try to use that analogy here, because Rutherford's going to do the same thing, except he's going to use, instead of marbles, he's going to use alpha particles. We've talked a lot about alpha particles. You're going to learn a bit more about them today. Alpha particles are particles that occur naturally in nature. And he fires these alpha particles at a very thin layer of gold. How thin? Well, gold is an extremely malleable metal, really thin. Like if you had a piece of that gold and you pulled it off of the edge of a table and you held it up, it would just almost fall apart. I don't know if any of you have ever looked at gold leafing, or do you know what gold leafing is? Sometimes they do it on picture frames. Sometimes they do it with the edges of books, the ends of the pages of the books. And when you buy gold leafing, it comes with these gold leaves between pieces of paper, and you actually have to lift up the paper, and then you use static electricity, use a brush, a real fine brush, to pick that up. It's so delicate. So this is what we're talking about. We're talking about very, very thin. Maybe 100 atoms thick, really thin. And what he does is he observes how these alpha particles interact. So here's a diagram. By the way, I have to be careful here. Rutherford didn't do this experiment. It's too bad he's credited with it. He came up with the experiment, but he had his assistants do it. A couple of scientists by the name of Geiger and Marsden. Geiger is the person who invented the Geiger counter, which detects radioactivity. And we have a Geiger counter. We're going to do some experimentation with it later in the unit. So what's an alpha particle? Okay, it turns out that an alpha particle is 2 protons and 2 neutrons bonded together. Okay. Later on in the course, well, by the time we leave for Christmas probably, you will learn that another name for an alpha particle is a helium-4 nucleus. But the bottom line is it's 2 protons and 2 neutrons, and these particles are emitted by radioactive radium. So this is his apparatus in a nutshell. This is the diagram or the photo or the image that you're looking at. And he fires the alpha particles, puts the radium in a piece of lead shielding and drills a small hole that the alpha particles can come out of, because this radium is emitting alpha particles in all kinds of directions. And alpha particles are bad for you. Alpha radiation can kill you. So he shields this from himself and his cat and anybody else who's in the room. And he fires a beam that way, and he detects where the individual alpha particles land. That detection screen is, you know, I have the cathode ray tube and you see that green dot. It's basically the same kind of idea. It's a piece of metal that's coated with a chemical that will give you a little flash of light anytime a particle that has charge hits it. So what they do is they set this up, they uncover it, and Geiger and Marsden sit around looking at the flashes of light. It's a little more complicated, but that's basically it. And they keep track of where the flashes of light occur and how often they occur in different locations. What do they observe? The first thing they observe, and I want to tell you so you can think about it before you start writing, is that almost all of the alpha particles, about 95% of them, go through with very little deflection. They're heading towards you and they just deflect a little bit. And the typical numbers that we give, although it depends on the situation, is that about 95% of the alpha particles are scattered within about a 10-degree deviation from their original path. Those numbers are going to depend on variables in the experiment. I mean, if the gold is thicker, you would probably expect those numbers to be different. If the alpha particles were moving faster and some other elements other than radium also emit alpha particles, and if you used a different source instead of radium, those alpha particles might have less or more energy. And we'll look maybe tomorrow at the fact that if they were moving slower, they would be deflected more. And there's going to be a reason for that. Actually, it won't be tomorrow. It will be probably Monday. So that leaves about 5%. Not all of the remaining particles, but almost all of the remaining particles are deflected through more significant angles. They're deflected between 10 degrees and 90 degrees. And I want to explain to you what that means. That means that if the alpha particles are traveling from left to right, they are detected on the detection screen on the other side of the foil, but they're detected at wider angles than 10 degrees, but not past 90. So what we say is a little less than 5% are deflected at angles greater than 10, but less than 90. These numbers are not important to memorize. They're there for you to think about the distribution of scatters that happen. And I can't tell you the exact percent, but it's less than 1% that's left. And I believe it's the number that pops in my head is like 0.0003% or something. It's a rare beast, but it happens. These are deflected backwards in some way. They're deflected through angles greater than 90 degrees. I think having had me as a teacher, you know kind of some of my philosophies. Normally, I'm not a big fan of having students write notes, but my experience is sometimes having you write this and think about it and having this downtime where you can just reflect on it is better than me just reading through it. Let me give you a visual, and you can connect these to your diagram at the top, because what I'm saying is that 95% of the alpha particles are landing in this kind of region. You know, it only shows 2 flashes of light there, but there's gajillions of flashes of light there. So if you wanted to, you could indicate those spots and put the number 1, because that was Rutherford's first observation. Little less than 5% are the ones that still make it across through the foil, not across, through the foil, but they're deflected further than 10 degrees away. So when they're watching this, they're seeing flashes everywhere, and they happen really quick. It's hard for them to keep track of. But they see, 95% of the flashing occurring in that one region, and then they see kind of a sporadic ping, 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 like 5%, about 1 in 20 flashes at bigger angles, and then every now and then, and it's so few. You could probably be watching this for 5 minutes and you don't see that's an exaggeration. For a minute without seeing one of these flashes behind not behind, I guess, in front of the foil. So that's what we're talking about. This last result was very surprising to Rutherford. When Geiger and Marsden started giving their data to Rutherford so he could write it up and take credit for everything, he actually chastised them and said, "You haven't set up the experiment right. There's no way this can be right." In Rutherford's words, he thought it would be like firing a bullet at a piece of tissue paper. An alpha particle is a fairly massive particle, and it's moving with around, 5,000-6,000 electron volts of energy. It should just go right through the foil. He didn't think there was anything in the atom that was solid enough for the alpha particle to bounce backwards off of. And that's going to lead to the idea of the nucleus. All right, so what's the conclusion here? Look, let me just put it to you this way, and this isn't in your notes. If 95% of the alpha particles make it through with very little deflection, then 95% of the atom is nothing really important. There's a lot of empty space. I know they're deflected, and this is where it gets more complicated, but it'd be like you rolling a whole bunch of marbles and 95% of them basically make it through. 95% of the stuff under the plywood is nothing. So we conclude that an atom is mostly nothing, which is kind of weird. Everything that's out here is mostly empty space. Okay? But since a very tiny number of alpha particles encounter something which causes them to basically be deflected back, there must be a very large concentration of mass somewhere in the atom, which occasionally alpha particles hit. And that means that that mass is really concentrated. It occupies a very tiny region of space because the chance of an alpha particle hitting it is very slim. If I had an alpha particle this big, and for those of you watching the video, I'm holding my fingers about a centimeter apart, and you fire from the back of the room, left side of the room to right side of the room, you fire a gajillion alpha particles, very few are going to come in contact with that object. Now, let me give you the details here, and then I will explain the rest of it. Basically, the Rutherford, it's sometimes called the nuclear model, sometimes it's called the planetary model, has a nucleus which is positive. So it has to have a positive charge. This is complicated. Why does the nucleus have to be positive? Because it explains why the alpha particles, even when they don't interact directly with the nucleus, are deflected a little bit. They're repelled. Alpha particles are positive. They're repelled from the nucleus. But they never really get that close because the nucleus is so tiny that most of them are repelled just a little bit, less than 10 degrees. The ones that end up getting a little bit closer to the alpha particle are going to be repelled more. And then that little tiny, tiny thing here, if an alpha particle, I'll show this to you. If an alpha particle is moving this way, it'll be deflected maybe like that. It's pushed away. I'll use a better color. It's pushed away from the nucleus slightly. If it were traveling this way, it would be pushed away from the nucleus even less. It's a KQQ over R squared force. If an alpha particle is heading this way, it would be deflected a lot. If an alpha particle is going like this, it might come back. But that window, that target that the alpha particle has to be close to come back is too small. So it doesn't happen very often. The only other thing that's left is for me to explain to you why the nucleus has to be positive. And the answer is because Thomson already discovered electrons are little tiny particles. And you need a large concentration of charge to deflect the alpha particles. But the electrons are distributed around the atom. So these are the key features. The majority of the mass is in the nucleus. The nucleus contains protons and neutrons. It's really a shame that they developed high school physics and we don't learn about the discovery of protons and neutrons. It's just missing. Let me finish this. Don't forget your question, please. The electrons orbit the nucleus at a very large distance. And the number of electrons orbiting the atom is equal to the number of protons in the nucleus because atoms are neutral. This diagram is not drawn to scale. The first thing is those electrons are not that big. This is the best diagram I could find that makes sense. Those electrons should be tinier. The other thing is the nucleus is really tiny. If you take a look at a hydrogen atom, okay, we're going to look at a hydrogen atom, and there's the nucleus of a typical hydrogen atom, which is just a proton. There's an electron in orbit around it. And the electron is in orbit way over there right now, on the far side of the room, on the right side of the room. Do you see the scroll bar at the bottom of this window? So I'm going to scroll so that this moves. Right? If I want to scroll vertically, I would do this. You can see the thing moving, right? I'm going to scroll, and I have to do this at my computer. I'm going to scroll horizontally until we get to the electron. And you watch that bar at the bottom move. So there goes the neutron. Watch the bar at the bottom. It is moving. It's just moving so little because this distance is huge, huge. The analogy that was given to me, and I've never bothered to crunch the numbers because I don't think it's that important, is that if you developed a model of the atom, a physical model where the nucleus was a basketball, the closest electron would be in Calgary. From here. That's how much nothingness there is to atoms. Now it depends on the atom. Okay, I'll give you some numbers here which you don't need to know, but which are useful in our conversation. The diameter of a typical run-of-the-mill atom is around that. And, I mean, it varies depending on the atom. And then those dimensions are much smaller than the diameter of the atom itself. The diameter of the atom can be anywhere from about 23,000 times to 145,000 times the diameter of the nucleus. So you can work it out with a ratio. I don't know how valid the basketball analogy is, but if you took the diameter of a basketball and multiplied it by 145,000, apparently you get the distance to Calgary. Now that was in Edmonton, and that was just some prof. I don't know if it's true. I've never checked it. You can check it out. I can see many of you are doing it right now, so what the heck? What's a basketball? 30 centimeters, maybe? Let's go 25 centimeters. 0.25 meters.
Is the numbers in the Pascal like the size of it, like 28.5?
I can't hear you, I'm sorry.
28.5, I guess. Is that like some of the basketballs like in the gym have numbers on them, and I think that's the diameter?
Oh, okay. Oh, really? Okay, so 0.285 meters. Times 145. I mean, this is for hydrogen. 1,000. Yeah, I think he was over-exaggerating a little bit. But still, it's 41 kilometers. So, from Edmonton to here, basically. Pretty close. So in the center of Edmonton, there's a basketball. That's the nucleus of a hydrogen atom. You're going to build a scale model for your science class. You're going to need a lot of room, right? You need to scale it down. Farhan, you had a question.
Okay, so an alpha particle is made out of a proton and two protons and two neutrons, right?
Yes.
So in Rutherford's mind, what was he sort of shooting at the gold foil if he doesn't know what those are? Like, because he doesn't know what the nucleus is.
He knows there are particles that have been called alpha particles, and based on charge to mass ratio experiments, he knows they're quite bulky. And this is going to be a recurring theme throughout much of what we do in nuclear physics, that you can identify new particles by looking at their charge to mass ratio. I'm not saying Rutherford knew what was in there. I'm saying we know what's in there. He knows they're very, very tough particles. They're very heavy particles. We will learn why we know the properties of alpha particles next week when we talk about alpha radiation, beta radiation, and gamma radiation. So unfortunately, because all of these things were being studied and learned sometimes independent of each other, there's not a nice seamless history to all this, which is why sometimes you'll learn something here and I'll go, well, we'll talk more about that later. All right, so now we're going to talk about the problems with Rutherford's model. And I don't want to spend a lot of time with this. In fact, I would say to you, your homework is as well as to get ready for the exam tomorrow. And I believe I misspoke earlier when I said and tomorrow when we move on. We're not moving on till Friday, right? So I would say, and I'll remind you tomorrow, that your homework for Friday is to read through this lesson, particularly this next part, to really get a gist of what's going on. So there are two serious problems with Rutherford's model of the atom. And one is that in the last unit, and this might be important for tomorrow's exam, anytime you have an accelerating charge, you will produce EMR. That's what Maxwell said. So if I have an electron that's accelerated by a voltage, I get EMR. If I have an electron trapped in a magnetic field moving in a circle, I'm going to get EMR because that's an accelerating charge. And what Rutherford is saying is these electrons in the atoms are moving in a circle or some kind of orbit. And according to Maxwell, that constitutes a changing electric field, which will create a changing magnetic field, which will create a changing electric field, which creates EMR. That's what EMR is as a wave. Can you picture it in your head, that diagram where we have an electric field going up and down and a magnetic field? I can't do that. Electric field going up and down and a magnetic field going in and out. That's EMR, but really, don't forget, the very first meaningful statement in Unit 3 that I told you is EMR is a form of radiant energy. It's energy. So according to Maxwell, an electron moving in a circle will create energy. Well, you can't create energy from nothing. It has to come from the electron, which means the electron should be emitting energy. There's two problems with this. One, every atom should be continuously emitting energy in the form of light and different forms of EMR, and they don't. I mean, the objects around us are not emitting light because you can see them. They're emitting light, well, they're reflecting light is what they're doing, right? So atoms don't on their own all the time emit light. So the electrons can't be accelerating, which is a real drag because then you're left with the conclusion that maybe the electrons are just kind of hanging there, which causes all kinds of other problems. But it is a problem. So in Rutherford's model of the atom, they're always accelerating the electrons. And if Rutherford's right, all atoms should always be producing EMR, which leads to the other problem. The electron should just spiral into the atom. And calculations show that if Rutherford's right, these electrons will spiral into the nucleus within about a nanosecond, which means all matter would decay very quickly. And yet, here we are having this conversation, and we're still here. So Rutherford's wrong, all right? There's another problem, though. And it cannot account for atomic line spectra. And I will show you some tomorrow. We will actually observe atomic line spectra. But when you heat up a gas, like hydrogen gas, it glows. And again, I don't want to show this to you today because I just want to get through the content and then we'll look at it tomorrow. So if I take a tube and I fill it with hydrogen gas and I apply a voltage, it glows. It glows pink. Hydrogen has a pink color. But if you were to look at that light through a diffraction grating to spread it out, because different wavelengths diffract by different amounts, you discover it isn't pink. It's 4 very specific wavelengths of light. It's called a line spectra. If you were to turn the page, I can show you the line spectra for hydrogen. This is it. Now, I decided to print this in color for you because normally I would say, and I want everybody to look up here, so this is what happens when you take hydrogen gas and you heat it up, you pass the light through a diffraction grating and you observe the colors. Remember when we did this with the light bulb and you saw the whole rainbow? You wouldn't see the whole rainbow. You would see 4 colors. And I would normally ask students, how many of you can see this line right here? Looking up here. It's pretty difficult, isn't it? But it actually printed out pretty good. And when you do this, you should be able to see it on paper. When you look at the hydrogen line spectra, and we'll do that tomorrow, you won't see it. It's too dim. But if you do it by getting in total darkness, it's very faint. Anyway, hydrogen, for some reason, emits those colors. And helium emits a different set of colors. And lithium emits a different set of colors. And every different element has its own fingerprint. So when you heat an element to a high temperature, oh, how many of you remember flame tests from Chem 20 maybe? That's what's going on. Except in chemistry, you're not analyzing the light in terms of wavelengths necessarily, not in high school chemistry, you're just using colors. In chemistry in university, you would do a spectrograph of that color to spread it out and look at the different wavelengths. So now that we've established that Rutherford can't explain why those lines of light occur, I'm going to briefly talk about 3 different types of spectra that you need to be familiar with how they appear and what conditions are necessary to produce them. The first one you already know. Remember when I turned on the light bulb and we were changing the temperature of the bulb by increasing the voltage? And you saw the 2 rainbows? Those 2 rainbows are called continuous spectra. I guess I have one more thing to explain here. How do you observe a spectrum of light? You need to take the beam of light and spread it out. And there's 2 ways to do that. You can use a diffraction grating, in which case you observe the light on the right-hand side of this where the long wavelengths are further away. This should be very familiar to you, this idea. This is called a spectrometer. All a spectrometer is a diffraction grating set up in such a way so that you can measure the angles. And in reality, when you do this, and I do have a spectrometer that I'll show you tomorrow, but it basically has the diffraction grating mounted on a screen. It has a little eyepiece here that you look through, and the eyepiece is on a swivel so it moves. And you look through there and you look and you look and you go, oh, there's a red color. And you then record the angle, which will allow you to find the wavelength with the formulas we've learned about for interference. Lambda equals d sine theta over n. And then if it's that hydrogen line spectrum that has only the 4 lines, you would start moving this and you would see nothing. You would see nothing, 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 nothing until you got to this one. And then you would look down on the spectrometer, on the table of the spectrometer, you'd read the angle and you could calculate that wavelength. And you would continue doing this. With a spectrometer, however, you could use a Prism spectrometer. And I'm not sure why we use them. It's the ones that we used in university. They're I don't know if they're more accurate. The problem is there's no formula to convert the angle to a wavelength. You have to use another resource. You have to use a data table. So it's really kind of a clunky method. Anyway, you could do the same thing with a Prism spectrometer. So now, everyone, in the last unit, I expected you to know that long wavelengths are affected more by diffraction and short wavelengths are deflected more or affected more by refraction. Did I get that right? I did. Now what I'm expecting you to be able to say is, what wavelength of light is affected most by a Prism spectrometer? So then you have to say, well, prisms cause refraction. Blue light refracts more than red. Another difference between these two spectrometers is when you use this type of spectrometer, you have to get at least 2 spectra. Spectra is the plural of spectrum. Because you're going to get an n equals 1 spectrum and an n equals 1 spectrum. You could also have 4 though, couldn't you? Because you could have the n equals 1 pair and the n equals 2 pair. With a prism spectrometer, you only ever get 1. So now, here are the 3 types of spectra. This is one you are familiar with. I started talking about this a minute ago, and then I realized I had to talk about spectrometers. When you have a solid object that's heated, can anybody tell me what we can call a solid glowing object? It's a black body. This is black body radiation. When you have a solid object that's glowing, it will produce what we call a continuous spectrum, a rainbow of colors representing every single wavelength in the visible light spectrum, assuming the temperature is high enough. My diagram here is just showing that we have a glowing solid. I've got a little aperture there, a little opening for a beam of light, a very fine beam of light to go through. It hits your diffraction grating, and on the right-hand side you would observe 2 spectra, and they would look like this. Just to make sure you were aware of what's going on here. The spectrum at the top would look like this. The spectrum at the bottom would be reflected. The red would be at the top. The blue would be at the bottom of the top spectrum. Is that right? Yes. A heated gas, and you have to take a gas that's, it says atomic, it doesn't have to be atomic. Some gas, so you take some substance and you go to a gas, it's probably an element, you heat it up, and then you pass electricity through it maybe to really heat it up. It glows. You've heard of or seen neon signs? Well, when you look at neon signs in businesses, they're not all neon. Neon has a particular color. Hydrogen has a different color. If you pass the light from a glowing gas through a tiny opening and then through a diffraction grating, I like using the diffraction gratings, and analyze the light over here, you don't get a continuous spectrum. You get a spectrum of light that's characterized by very specific wavelengths. Now, these are called lines. The only reason they're lines is that the slit is linear. Okay, so the light is coming from my nose, it's hitting this little tiny opening, and it's giving you a beam of light that's flat coming towards you. So when we spread it out, you're going to get a red line and a blue line and all those different lines. So this is called an emission spectrum. And again, leading up to tomorrow, or Friday rather, this is the emission spectrum for hydrogen. The one you're looking at is the emission spectrum for hydrogen. You cannot change this. No matter what you do, hydrogen only ever produces those 4 wavelengths of light. And you can measure the angles and determine the wavelengths, and we'll talk about that Friday. The third spectrum is called a dark line spectrum. And it's produced, get this, it's not really produced. Well, in order to get a dark line spectrum, you have to start with a continuous spectrum. So if you take a look at what I've got in the diagram, I've got a glowing solid, and the light coming off of that glowing solid, everybody, is a continuous spectrum. So that glowing solid, that black body, is producing every wavelength in the visible region. And what we do is we pass that light through a cool gas, through a gas that's at a low temperature and a low energy. And when we observe through use of a diffraction grating spectrometer, the spectrums, or spectra, what we see is a negative image of the bright line spectrum. instead of seeing a bright line where that red line is for hydrogen, you see nothing there. And by the way, that dark line spectrum you're looking at is the dark line spectrum for hydrogen. I would have to say, I think, yeah, I'm pretty sure, that dark line spectrum is contrived. That's not an actual photo of a dark line spectrum. In other words, I think what I did is I took the continuous spectrum and put black lines in the right places. Okay, it's a little more subtle than what you're looking at. So this is called an absorption spectrum or a dark line spectrum. I don't like saying it's produced by a cool gas because the cool gas isn't producing it. The cool gas is swallowing up particular wavelengths and allowing everything else to pass through. And I think this is the important point to end today on. Hydrogen, for some reason, is only ever capable of emitting these particular wavelengths of light. There are certain, this is just an analogy, there are certain holes in hydrogen where these things can leave. And they are the same holes that will allow them to come back in. So there's something going on, which is a really bizarre thing because hydrogen is a proton and an electron. How can a proton and an electron behave in some way that always do this? And you know what this is saying? These are the only wavelengths hydrogen will absorb. So if you take this color of light and shine it on hydrogen gas, the light just goes right through. The hydrogen doesn't want it. It won't take it. It will only accept certain wavelengths. I'll tell you right now, it will only accept certain photons, and it will only emit certain photons. And that's going to lead us to the Bohr model of the atom on Friday. So that gives you guys about 10 minutes here to go over any extra stuff for tomorrow's rewrite exam.